All right, guys, welcome to our video on mole conversion. So we're going to be doing a little math here. Before that, got a little interaction between Yoda and Skywalker. He says, "Yes, young Jedi, I too sense a great disturbance in the Force." That's the best Yoda I can do. "May I suggest that in the future, you go a bit easier on those burritos from the dark side." Okay, had a little inspirational quote, but we'll move on. Okay, check this out though. You guys don't have to write this down. 1 mole of rice grains. You guys, when you guys hear 1 mole, you guys remember what number should come to mind? That is 6.02 times 10 to the 23rd. You guys like, right, for example, I'll show you. Okay, sorry guys. So let me just show you guys right in here. So in this flask here, I have 6.02 times 10 to the 23rd atoms of copper. I do. And there's a technique I can use to do that, but we could talk about that, and we'll kind of incorporate that in today's lesson. What we're seeing here is that 1 mole of rice grains is more grains than all the grains that have been grown since the beginning of time. You guys think about all the rice. Think about the rice that you eat. If you just eat a bowl of Rice Krispies, and you were to count every rice grain in a bowl of Rice Krispies, you're talking thousands, right? Then just think about all the rice, for example, they eat in China, right? That's not a racist thing. That's just, right? The rice is a basic staple of food in China. Think about all the Chinese people. You guys know there's like 1.4 billion Chinese people. Think about all the rice that's eaten in one day. Now think about all the rice that's ever been eaten by all the people in the world since the beginning of time, and yet this number right here, 6.02 times 10 to the 23rd, can you guys even see that number? Yeah, you can barely see it. 6.02 times 10 to the 23rd, that is a larger number than all the grains of rice that have been grown since the beginning of time. And you know what's even more remarkable? There are more atoms of copper in this flask right here, because there's 6.02 times 10 to the 23rd. There's more atoms of copper in this flask right here than there are grains of rice that have been grown since the beginning of time. You guys, and you're supposed to say, dang! You guys, and what are we supposed to kind of gather from that? Not only the magnitude of that number, but that just shows you how stinking small atoms are, such that you can get that many atoms in a very small amount of space. We'll move on from that. He says, "Hi Gina, Fang," that's his dog, "Fang and I are making a pot of chili, and we were wondering if we could borrow just a couple of things. They just need a couple of things." She says, "Sure, what do you need?" He says, "Well, first of all, we need a pot, and then we need some chili." You just need 2 things. Okay, you guys write this. This is like a roadmap. This is going to help us in our conversions. You guys want to refer to this map whenever you're doing conversions. It's going to allow us to convert from WT, is just short for weight. That's the weight in grams. Notice the units in grams. We've got volume in what's called STP, that's standard temperature pressure. I wouldn't worry too much about STP, but we've got the volume of the gas. And then we've got the number of atoms and molecules. And you guys see right smack dab in the center of our map is moles. You guys think about it, much like they say all roads lead to Rome, all conversions lead to moles. So we're going to show you guys how you can use this map to solve problems and convert from one value to another. So whenever we're going to convert from weight to moles or moles to weight, you guys see we use what's called the MW. That's short for molecular weight. Another word for that would be molar mass. We learned that in the previous lesson. And I give you guys a hint. You're going to use your periodic table. You're going to find the molar masses in the periodic table. That's going to be, you're going to be looking at the atomic masses. If we want to convert between moles and number of atoms or molecules, we already know that conversion. Remember, that's the conversion we talked about right here. 1 mole is 6.02 times 10 to the 23rd. So we would use that if we're converting. And then the last one, this is a new one, guys. 1 mole, and this is only for gases. 1 mole of a gas, under standard conditions, occupies a space that's 22.4 liters. So, for example, so in this box here, I have air molecules. That's all it is. It's just a cardboard box. I have air molecules. And really, and I'm pretty much under standard conditions. We'll talk about that next semester. But I have 6.02 times 10 to the 23rd molecules of air in this box. So the question is, under standard conditions, how big of space will that many air molecules or that many gas molecules take up? And you guys guessed it, this box is 22.4 liters. So I'm going to put it like this. So you guys write that down. 1 mole occupies a space of 22.4 liters. Okay, so that's just the fact that we just need to know, and then we'll use that. Okay, so let me show you what kinds of problems we can solve as a result of that. So, for example, let's say Okay, so you guys write this down. What volume at STP, once again, these are just standard conditions, don't worry too, will 0.1 moles of carbon dioxide take up? So for example, let's say I blow into this balloon. You guys remember, besides Mr. Willison's hot, funky breath, it's primarily carbon dioxide. So let's say I blew in that balloon 0.1 moles of carbon dioxide, okay? Let's just say I did. What do I want to know? I want to know what's the volume that it takes up. So there's 0.01 moles of carbon dioxide. What volume will it take up? So this is how you guys should typically do it. Okay, so I'm going to let that out. What you should do is, remember, it's unit analysis. So we start with, oh, you know what? Let's go back. Okay, so basically, I'm going to just write down, I have 0.1 moles of carbon dioxide, and I want to know the volume. You guys see that? I kind of just take information. And then you guys, what we do is then go back to our map. So we're going to use our map. Okay, so then you guys kind of look where you're at on your map. So notice, the information we started with, so here's what you do. Remember, we're going to use the analysis. Remember, we always do the endpoint first. What do we want to look for? What do we want to find? We want to find the volume. You guys remember, what's a volume typically measured in? You guys should remember it's liters. So we want to find out how many liters of carbon dioxide. If I had what? What did I start with? 0.1 moles of carbon dioxide. So now check this out. I basically want to go from moles to liters. So now I use my map. So I look on my map. Okay, where am I starting? So I look at my unit. Where am I starting, guys, on my map? Would you guys agree? I'm starting here at moles. And then where on my map am I going to? I want to figure out liters. So where am I going to go? Hopefully you guys realize, oh, I'm going to the top left here. I'm going to volume. So now you check it out, guys. You think about how many roads does it take to go from moles to volume? Doesn't it just take one road? So that means it's just a one-step unit analysis problem. And then you guys, what's my link between moles and the volume? It's this fact right here. 1 mole occupies a space of 22.4 liters. So look, I have moles on top. So which one of those do I want to put on the bottom so they cancel? You guessed it, I want to put the 1 mole. So 1 mole of carbon dioxide would occupy 22.4 liters. I put that on top. And you'll notice now, check it out, what cancels. You only cancel out the units. Mole on top, mole on bottom cancels. What's the only unit you're left with? Liters. Good indication I'm doing it right. 0.1 times 22.4. I'm wondering if you guys, can you guys even see that? Yeah, you guys can see it, barely see it. 22.4 liters. Basically, I just moved, you guys could just multiply that, but basically you just move the decimal over 1 point, and it's 2.24 liters. When I have 0.1 moles of carbon dioxide in that balloon, it's occupying a space, it'd be bigger than that, of 2.24 liters. You guys see, it kind of makes sense, because look, if 1 mole occupies a space this big, you guys think about it, what's 0.1 moles? Those of you guys are good with math, you guys know that's 1/10. So wouldn't 1/10 the amount of carbon dioxide occupy a space that's only 1/10? That's about 1/10 the size of that box. All right. Guys, let's do another one. You know what? I'm going to skip, and just to make this video a little shorter, let's go with this. I'm going to just make up a problem. Let's say, you guys think about it, you guys should know, we have a can, it's just an empty soda can. You guys think about it, what do you think a can is made up of? Obviously you got a little bit of paint there, but it's primarily a what kind of can? You guys should know, aluminum. So what does an aluminum can consist of? Pretty much aluminum atoms. Let's say, for whatever reason, I want to know how many aluminum atoms does this can consist of? How many aluminum atoms? So the question is, how would I figure that out? Okay? So basically, in my situation, I would set up a unit analysis problem. You guys remember what you do. Guys, I'm going to do that. Let me see if you've got space. Yeah, you know what? We can do that right here. So, you guys, look, I want to figure out how many aluminum atoms. Okay? Now, the question I have for you guys is, if you guys were in the class, what could I figure out about this can right now? Like, I don't know how many atoms. It's not like I can count the number of atoms. What could I do? What could you do with a can that you think could maybe help you out? I don't know if you guys can see down here, but I have a scale. So what do you guys think? I could get the what? Couldn't I get the weight? I could put it on my scale. I measure the weight. Let's say it, well, I'll just look, weighs 2.1 grams. So in that can is primarily aluminum, so I'd say I have 2.1 grams of aluminum. Now check it out, guys. Look at how, now I need to go from grams to atoms, so then I can use my math. So if I'm starting at this unit grams, let me see if this is all within, yeah, you guys can see it. If I'm starting with grams, guys, where on my map am I starting? I'm starting at weight. And then look at what unit I'm going to. I'm going to atoms or molecules. So where am I looking? Where am I going? You guessed it, I'm going down here. Now you guys look how it's different. Question is, how many roads does it take to get from weight to number of atoms? You guys check it out. Once again, what did I say? All roads lead to moles. So you got to go 1, 2. This is going to be a 2-step problem. And you guys, hopefully you'll see, the first thing you have to do is convert from weight to moles. And you remember how you do that? Use the molecular weight, or otherwise known as the molar mass. And you remember I gave you a hint on the previous slide that that is found on the periodic table. So what would I do? I look on my periodic table. I don't know if you guys can see, but I find aluminum, because we're talking about aluminum, and I look at its weight. Its weight is 26.98. If I round that to the 10th place, that would actually round to 27.0. Remember what the units are when you say that off? 27.0 grams per mole. What that means is 1 mole of aluminum weighs 27 grams. That's what you figure out. And so look, I use this information right here. I just need to know which one goes on top and which one goes on bottom. So I look at my unit that I'm starting with, grams, it's on top. So the only way that grams is going to cancel out is if I put the grams on the bottom. So I'm going to put 27.0 grams on the bottom is equivalent to 1 mole on top. And notice that grams cancel. So if I were you, I would cancel the units as you're going along. So now you guys see, if I were to stop at this point and go 2.1 divided by 27, I would get my answer in moles. That's where I'm at right now. I'm not there yet, right? My destination is here at the bottom, so I got to keep going. So now how do I go from moles, where I'm at right now, to number of atoms or molecules? I use this fact right here, 1 mole is 6.2 times 10 to the 23rd. So then I just take that information and put it here. I just need to know which one goes top, which goes to bottom. 1 mole is on top, so when you guys agree, I'd want to put the 1 mole on the bottom so they cancel. And that's equivalent to 6.02 times 10 to the 23rd atoms. We're talking about atoms here, right? If it was like water, it'd be molecules or something, but we're dealing with individual atoms. So moles cancel, and now you guys see, look, the only unit left is atoms, which is what I wanted. Good indication I did it right. So what am I going to do? I'm ready to punch some numbers. So I'm going to put, you guys remember, everything on top you multiply, everything on the bottom you divide. So I'm going to go 2.1, multiply by, you can multiply by 1, it'll just be times 6.02, and I'm going to remind you guys, when you're using a calculator, a typical calculator, you don't put times 10, you press a button called EXP or EE. I press EXP, which means times 10, and then I just put 23. So I didn't have to put the times or the 10, I just pushed an EXP button, an exponent button, and then I put 23. And then, check it out, then I'm going to divide by, the only number really on the bottom that I got to worry about is 27. And what do I get? I get 4.7 times, and you guys got to be careful, you guys got to look and see if there's exponents at the end, times 10 to the 22nd. On my calculator, I know you guys can't see it, but it says 4.7, and then it says to the 22. It's not 4.7 to the 22, it's 4.7 times 10 to the 22. The calculator just assumes that you would write it properly. So you guys look, if you see, that is, what we just figured out is, there are 4.7 times 10 to the 22nd. That's like what did we say? What did we say this was? Did we say that's like 602 sextillion or something like that? So this would be like 47 sextillion atoms of aluminum just in this light aluminum can. All right, guys, so this is a little example of mole conversions, how we convert between different units depending on what it is we wanted to find. One last thing. Remember I was saying that there's more atoms of copper here in this flask than there are grains of sand or grains of rice that have ever been grown. Somebody say, well, how do you know that there's 6.02 times 10? I said there's 1 mole of copper there. You guys think about what do you think I did? All I had to do to get 1 mole of copper is I look on the periodic table. I see the molar mass of copper is 63.6 grams per mole. So what do I just do? I just use my scale. I pour copper in there until I have 63.6 grams. If I have 63.6 grams, I know I have 1 mole. If I have 1 mole, I know I have 6.02 times 10 to the 23rd. All right, guys, that's all I got for you guys. We'll see you next time.